Hello YouTube, RJ. Today I want to continue on working on the voltage calibrator circuitry, and I've got that demo board we built in a previous video where we put the 3094 LT3094 on 3045, I'm sorry, LT3045 positive voltage regulator, and the 7809, and we did the noise comparison. But I want to go ahead and finish up this circuit and test it out. And one of the main things is we're going to be looking at an LT1010 today, and that is the op amp device that's going on the front end from the battery. And its purpose in the circuit is to take that wide spread of that 24 to 29.5 volts the battery's going to put out. But I need a positive and negative for some of the op amps. So we're going to make a supply splitter, as they call it. Here's the data sheet. I'll pop it up where you can see it a little better. But this is the data sheet on it, and a lot of great information in here. This is the device we're going to be using, the TO220-5 model. And what we're going to be building, and I'll pop it on the screen again so you can see it a little better, but it's a supply splitter. And there's actually a circuit outline for this device in here. We're doing a little different, but basically the same exact thing, to take a DC supply of, in this case, a 24 volt to 29.5 volt battery. We're going to put it across this device, and it's going to generate us a virtual ground dead in the middle of those two. So let's say it's 24 volts at the moment. It's going to create a virtual ground at half of the positive voltage. It's going to give me a 12 volt reference, and we're going to make that a virtual ground. It doesn't regulate the voltage in any way. The voltage will drift based on the battery voltage, but it'll always be half of this point and this point. So your positive and your negative battery, it's going to give me some, whatever the middle of that is. It'll move as these shrink. This will move and keep me exactly half of the positive voltage. Now, why do we want that? Well, we create a virtual ground from that. If you take your meter and you measure from the virtual ground up to here, you'll get half the volts of the battery. Let's say it's 24 volts, you're going to get 12 volt positive. But if you take your meter and you continue to use that virtual ground as a ground, and you go over to the ground or the negative side of the battery input, you'll see negative 12 volts. So you get a positive 12 volt and a negative 12 volt. That's what a supply splitter does. That's what its job is. So that's what we're going to do. So the plan here today is I'm going to go ahead and put that in, put the couple caps that go in, the voltage divider resistors in. You can see in the diagram here, there's basically what you're doing is creating, well, it's not basically, you're creating a voltage divider to give you a halfway point, and you're inputting that in to the op amp and saying, this is the voltage I want out. So then what happens is you get that voltage. So if it's a even resistors, as in the case here, 10K and 10K, you're going to get half the voltage. Well, why don't you just use a voltage divider? Well, the problem with the voltage divider is if you set your resistances up high enough so that you don't have a lot of wasted continuous drain on the battery, then what happens is you have no current available. You can't pull any current out of here. But if you use that to feed an op amp, the op amp becomes a buffer. And the op amp says, okay, I'll give you that voltage, half voltage you're asking for, but I'll give it to you with some oomph. I'll give you some current. So that's what we're going to do. First thing we're going to do is we're going to get our LT1010 on the board. Get the voltage divider in here, get the capacitors in there, and then we're going to test it and make sure that when we put 24 volts in, we get 12 positive and 12 negative off the virtual ground. I'm going to go ahead and set up, get the LT1010 on there. I'll probably just time lapse through that and come back and we'll do a little testing on it. So be back in a couple of minutes. All right, so I've got it together. Got the LT1010 on, 2 input capacitors, my 10K voltage divider here. So if everything is correct, I should be able to put power, 24 volts. We've got 24 volts on the power supply. Should be able to put our 24 volts on here. Sure enough, it's getting warm on us here before we And we can take a look on our meter. I want to see what's going into this LT35. So if I go here and here, what am I getting? 11.46. Okay, what's going into this thing? 23.9. Let me adjust that to 24 exactly. We adjust the supply to 24 exactly so we can better tell what we're doing. Touchy here. See if we can get it. How close I can get it. Analog power supply. Ooh, really close right there. We're going to go with that. 23.9999. We'll do it. Okay. So what are we getting for input here? 11.491. Okay, so not exactly half. What are we getting here? Negative 12.5. See, that's the offset. So the voltage divider probably isn't perfect, or we've got a little bit of offset on here. So wonder what I'm reading voltage right in the middle here. Let's see, that would be right here. Okay, we're reading 11.6. So yeah, it's not exactly dividing. We're not getting exact division right here. So my resistors might be a little bit off. So that's a little bit of error there. It's going to be 1 volt offset. Interesting. See what our output of our regulator over here is. 8.7 basically. That's what we were getting before from it, if you remember. I need to tweak that resistor to get the voltage I want out of it. I might research that a little. 1 volt seems a little more than what I would have expected. 12.37 is not too far off a half. So if 12.37 is coming out to the LT1010, I would expect it to be trying to hold the output. It's actually trying to hold it at 11.48, but the input to it is, you don't hear. The divider input to the LT1010 is 12.37, but what we actually see coming out on the virtual ground is 11.48. Wonder why that is. It's almost a volt difference. I'm going to research that because I would not expect that much of a difference. So let me do a little research. We'll come back. I'll let you know what I found, and we'll try to figure this out. I would like to see it a little closer to on the money. So I'll be back. Okay, after a little research, first thing I did is I removed all of the voltage regulator circuitry off here because I thought maybe there was something going on there. And I added some resistors just to put a light load on the LT1010 in case maybe what we were looking at is an issue with not having the load on there. As I'm sure you're aware, sometimes that can cause a problem. A lot of circuits expect a load to regulate correctly. And that didn't change anything. Our voltages offset was still almost a volt. Did not change it much at all. Now I did expect that you might have some offset in this circuit, but I didn't expect half a volt. That seems pretty, I mean, you're talking a volt total, but I'm talking, I did not expect that kind of difference. So I went and did a little reading, a little research, went back to the data sheet. This circuit is almost identical to the circuits in there. I pulled the 2 caps off, input caps, thinking maybe I've got a partial short under them or something, just to be sure. Nothing changed. And then when I was researching, what I started coming across is this LT1010 requires a certain amount of, it needs a stiff voltage reference. If you, with the 10K resistors in there, the amount of current and how, it's just not a very stiff input. It's easy to pull that voltage around. It takes very little current draw to make that voltage move. And this can create a problem with the LT1010. So the things that came along was basically the circuit that they show for a supply splitter in their data sheet is really not a usable circuit. I would not use it for things. It turns out the better way is, number one, you have to have a stiffer input. So if you're going to use a resistive divider, you either need to have much lower resistance resistors in there, okay, which of course is going to waste a lot of power because that voltage divider is going to be running current through it all the time. You get a stiffer voltage reference into the 1010 by going to lower resistance. Or most of the time what the designers do is put an op amp as a buffer in front of the LT1010. Of course, most op amps can't handle much current. They're not going to give you a lot of current out, but what they do is they buffer that resistor divider so nothing loads it and makes it move around, and then you supply the output of that op amp, putting out the half voltage, the split between the rails. You input it just as I am here with the resistors. You do that to the LT1010, and this gives you a circuit that will have very low offset and it'll be much more stable. So obviously I can't do that on this board right here, but what I did do is I dropped the resistors to 1K. So a total of 2K resistance across there. So I think you'll see that if we take a measurement now, it's a lot better. It's not perfect, but it's a lot better. So let's get on here and see what we get. Okay, we're getting 11.893 on this one. And on this one, we're getting, this one's a little tricky to get onto for some reason. We're getting 12.1. So we're down to about 0.3 of a volt from a volt. So we're much better, but we're off some. So I'm thinking, since I want this right, I'm thinking what I'm going to do is I'm going to redesign the circuit for my board. I'm going to put an op amp in front of it. So I'm going to go back to the drawing board on that. And this is why I always say you design a circuit, you always want to check it out before if you build a whole device like a voltage calibrator, that's going to be very expensive, a lot of circuits, a lot of things in it. It's really best to play with it on a modular level. Design your circuit totally out so you know what you're doing, and then start taking circuits and testing them like I'm doing here. Because this kind of thing could ruin our day if we built this whole thing and found out, oh, this is just not going to work. So now I have the easy opportunity to go back and redesign this circuit, get this circuit working just the way I want it, and we can go from there. I make mistakes. Everybody makes mistakes. I like to show my mistakes. I want you guys to see that it's not abnormal to build things, look through data sheets, try to build things and run into issues. And these little things will trap you up. Now, there's probably a lot more seasoned guys out there that have worked with this stuff much longer than I have that probably go through and build these circuits and don't run into these problems. I've never met any of them, but apparently, I mean, Dave from eevblog, he shows his mistakes too. We all make them, believe me. So these are good mistakes. When you make these mistakes, you learn and you have the chance to go back and fix it. What I'm going to do is drop back, redesign this, and we'll go from there. We'll try that circuit out. We'll make sure it's doing what we want before we move forward. This process of building this voltage calibrator is not going to be a really quick thing. The big boys, HP, Agilent, Keysight, they don't build a new scope in a couple weeks. They spend sometimes years designing these things. So, hey, thanks for hanging in with me. I hope you guys learned something from this. I know I did. And most of all, do me a favor. If you like the video, hit the like button, help me out. It's hard to, as a little channel, it's hard to get out, especially electronic channels. Very hard to get out there and get pushed by the algorithm. So a little like will do so much for me. If you haven't subscribed, take a moment to subscribe. Most of all, hope to catch you in the next video.